we are in beautiful northern Utah. We're in the Provo Pass, and we are in a late model JK with a LT1 10-speed. What else? Today we're in a late model JK with an LT1 10-speed. Great combination, as you all know. I actually got a lot of response when I talked about emissions in a previous video. What's legal, what's not legal? Guys are confused. So I'm going to try to make a little bit of sense of this mess. I was an emissions inspector for over 20 years, and I was a high-level emissions inspector. And I also work in California, so I know a little bit about the law. A lot of guys say, oh, I don't got to worry about emissions where I'm at. Well, the reality is, if you live in the United States, we're all under federal law, or the US EPA regulations. And here's the basic regulations from the US EPA. The donor engine must be from the same year or newer than the vehicle you're putting it in. Now, there is some ambiguity to that because there are what is called engine families. So let's just take an LC9 that ran from 2010 to 2014. That's a 5.3 LS. They're all of the same family. If you were to go to GM and buy an LC9 for a 10 Silverado, it's going to be the same engine for a 15 Silverado. And this would be a good time to mention that if you look under the hood of your JK, you should have something called a VEC, or a Vehicle Emission Certification decal. That decal must have three things on it. One, the model year of the vehicle. And guys get confused on that sometimes because they'll look in the door jamb and it'll say it was manufactured in 9 of 14, so they think they got a 14. But then when you look at the VEC, it will say this vehicle conforms to US EPA standards for 2015. So 15 vehicles were built in 2014, and it's important you identify what year your engine is. The label on the door jamb is just going to say it meets the emissions requirements as of the date of manufacture. But the model year still could be a year later if you got a late in the year build. The second thing that must be on the VEC is the engine family. So if you got a 4-cylinder turbo or a V6, whatever it is, it's going to tell you the liters and identify the engine family. That's pretty common sense. The third thing that's going to be in the VEC is federal or California, whether the vehicle was certified to federal standards or California standards. And there still is a difference even today. Even though more and more states are going over to the California standards, you can still find some federal vehicles. And the way you'll know is you'll see phrasing something like this. It'll say this vehicle conforms to US EPA and California, or it'll just say US EPA standards. And if it doesn't say and California, then you most likely have a federal vehicle. The rule in California is if you're going to do an engine swap and you have a California vehicle, then you have to put a California engine in, because the emissions are a little bit more strict. The exhaust is a little bit more intense. So be aware of that. Now, where it gets a little confusing is the US EPA says you have to bring over all the hardware and software from the donor vehicle into the host vehicle. And that is open to interpretation, and that's where we run into issues. Referees in California and G2 inspectors out here in Nevada, and there's labs like in Colorado and Arizona. How are they going to interpret that? And let me back up a little and kind of talk about what's happened over the last few years. I've been doing engine conversions going on 40 years. I mean, way back in the day in the 1970s and 80s, I remember you take it into the California emission station, the state-run program that was a complete disaster, and the guy would put a ball bearing in the hose going to your vacuum advance unit on your distributor, and they call that a NOx device so that it wouldn't advance the timing. I mean, things have really changed. So the inspection process got pretty intense in 1990 with Bar 90, but we're not going to talk about that. We're going to talk about Bar 96, because Bar 96 is the Bureau of Automotive Repair 1996. I don't have a lot of nice things to say about the BAR. I've worked with them, and I've also realized how incompetent they can be, and that's going to be in a different video. In 1996, the federal government standardized testing to a certain degree. What they did is they told manufacturers they had to run a protocol that was approved by the government, that is the computer language, so that standard analyzing machines could communicate with, and they had to have a standard data link connector, or DLC. Of course, the vehicles have to have an MIL or a CEL, that's the malfunction indicator light or check engine light. That was standard all the way back to OBD1 in 1981. And there's some other rules, like the data link connector has to be visible. I find that sometimes manufacturers don't follow that. I remember back in the 90s, Acura and some of the others that put the data link connector behind the ashtray, so you had to pull the ashtray thing out, and we actually had manuals how to find the data link connector, but now pretty much most manufacturers have made them obvious. So OBD2 testing is pretty simple. Basically, you have onboard diagnostics. You have multiple monitors. There could be 3, 4, 5, 6. I think it goes up to 9. Now, there's some monitors that don't apply to a lot of vehicles, like air conditioning, but the engine performance monitors, like misfire, catalytic converter, O2s, those are very important. So since the onboard diagnostics 2 testing began in about 1996, the emissions programs relied heavily on the onboard monitors to test the system. If the onboard monitors completed and you had no trouble codes, there's a pretty good likelihood that your vehicle is running fine. If you have a check engine light and a trouble code, then of course you're going to fail if that code is related to emissions and you have to have it fixed. If the monitors aren't set, I think this goes state by state because I've seen different states handle it separately, but usually you're rejected, meaning it's not a fail, it's not a pass, they're just telling you that the monitors haven't set. So you have to go back and have the test done again after the monitors do set. Monitors set after drive cycles, and we talked about that before. Some monitors will set right away, like misfire usually sets pretty quick, but other monitors like EVAP can take days, and what they call drive cycles, where you have to see temperatures go below a certain value, and the intake temp and the coolant temp have to be within a certain value compared to each other. Usually it's an overnight test. Some of these use what they call a diurnal vacuum. They don't have vacuum pumps. The earlier Jeeps had what they called an LDP, a leak detection pump, which the California bar has a hard time identifying. I had to train them on that. The leak detection pump would pull the system into a vacuum for leak testing. And there's gross leak testing, like a big leak, like a gas cap's been left off or an O-ring is shot. There's small leaks. And the small leaks are the ones that are hard to test for because those leaks can appear after hours of sitting overnight. So the diurnal testing basically uses the natural vacuum created, NVLD, natural vacuum leak detection. So there's a certain amount of vacuum that gets built up in your fuel system after you shut the engine off, and it uses that for testing. The Jeep Wrangler JK has what they call an ESIM, or a EVAP system integrity monitor, but basically what it does is there's a switch inside that white thing on the side of your EVAP canister, and based on the vacuum, that switch is either open or closed, and then they can run their tests based on that switch position. Now the newer JKs, starting in about 12 with the Pentastar, are actually running a fuel tank pressure sensor, an FTP, which gives real-time fuel tank pressure or fuel system pressure or vacuum to the computer. Now, GM's been running that for many, many years, along with a vent solenoid that is actually controlled by a computer, where Chrysler is using a dumb valve in the ESIM. It's just a spring-loaded valve. Before we get too far into it, I'm going to mention the 5 basic tampering devices that we would inspect for during an emissions inspection. First one sounds simple, and that's the gas cap. And the gas cap is a very important part of the emission system. Back in the old days, gas caps weren't sealed. They had a vacuum and pressure relief valve built in for obvious reasons. When the fuel level went low, it needed to let air in. When the fuel pressure in the system built up high, like let's say it was a hot day in Los Angeles and you park your 69 Camaro on the side of the road with a full tank of gas, pressure is going to build up in that tank and you don't want the tank to explode, so you have to have a relief valve. Manufacturers learned early on to leave a gap in the fuel tank. What I mean by that is, rather than have the fuel tank fill all the way to the top with the fill tube, they would put the tube about 10 to 15% below the top of the tank. By doing that, it left an air gap on the top that allowed for some expansion of the fuel, and that's pretty standard today. So the fuel cap does have an important job, and back when I was doing emissions tests where we checked for tampering, we actually had a little tool that we would screw the cap onto, and we would check the cap for pressure and vacuum. The next thing is pretty simple, and that's the fuel restrictor. The fuel restrictor is pretty obvious. We ran leaded fuel for the longest time here in the country. Leaded fuel was kind of an easy way of making the engines last longer, valves last longer. It's a lubricant. The problem with lead is we all know that it's toxic and it's bad in paint and gas and everything else. So when they eliminated the lead, they had to have a way of not allowing you to put leaded fuel into your tank. So they put a fuel restrictor on, and the leaded nozzles were a larger diameter. That way you couldn't put a leaded nozzle into your tank. Now, of course, guys punched them out and did all sorts of other stuff, but that's what it's there for. The remaining 3 tampering devices can be a little bit confusing, but I'll try to explain them as simply as I can. And when we used to give what was called the practical test at the emissions lab, they want the shortest answer possible for what does this emissions device do. They didn't want a dissertation on how it works and all that. They just wanted a short answer. So first let's start with secondary air, or secondary air systems. And I think it's one of the most complex. What does secondary air do? Completes combustion. How does it do it? By putting oxygen into the exhaust system. Let's not get too complicated here, but basically if you think of a fire triangle, you have a campfire. You gotta have wood, which is your fuel. In the case of an automobile, it would be hydrocarbons and carbon monoxide. You have heat, which in the case of a campfire is probably going to be a match. In the case of an automobile, it's going to be a spark plug. Diesels are a little bit different because they basically run off pre-ignition, but we're not going to talk about that. And then the third part of the triangle is obviously air or oxygen. All of you guys know that the more oxygen there is around a fire, the hotter it's going to burn. And if you starve the fire of oxygen, it's not going to burn. And that's exactly what you have in the exhaust system. You have unburned fuels, which is carbon monoxide. That's 1 carbon and 1 oxygen atom. You have hydrocarbons, which is basically raw fuel. Because remember, these engines, while really efficient, they're not 100% efficient. So some of these bad gases get out into the exhaust. So you got fuel, and obviously you got heat in the exhaust. What are we missing? We're missing oxygen, or air. So the job of the air system is to put a little bit of oxygen into the exhaust in order to complete combustion. Light that stuff off in the exhaust, and that way it doesn't get into the converter and out into the atmosphere. And there was a lot of different ways created to put oxygen into the exhaust system, and it's always a little bit tricky because you're working with an exhaust system that could be running at thousands of degrees, and you got to pump air into it reliably, but you don't want that air to come back, so we had check valves, because if the hot exhaust gas came back into the system, it would destroy it. I don't know if you remember the old Ford diverter valves were made out of plastic, but when the check valve would fail, the vehicle would start backfiring, and then the plastic diverter valve would melt and just drip off the engine. In any event, there were basically 2 secondary air systems. One was pump air and one was pulse air. And pump air is pretty explanatory. They put a smog pump, and you guys remember that word if you've been around long enough, the smog pump. They started putting them on Corvettes and Mustangs and pretty much everything back in the late 1960s through the 70s and even the 80s. And I want to mention that the engines back then just weren't as efficient. Remember, most of the engines that Ford, Chevy, and Chrysler were putting out in the 80s were designed back in the 1950s, when emissions really wasn't that much of a concern. So these engines really weren't designed from the ground up for emissions like the modern engines. The modern engines are designed from the ground up to take into account emissions. Therefore, we can eliminate a lot of these tampering devices. Like EGR valves are pretty much non-existent anymore in GM engines. Chrysler still runs them, but it's the overall package that reduces the emissions and how the manufacturer goes about that. So getting back to the secondary air system, you put a little bit of oxygen in the exhaust, and that burns off the remaining bad gases. Air systems got a little bit out of control. They went to what they called air management valves that would, like when you would start your vehicle up, they wanted to heat the catalytic converter up as fast as possible, and they also wanted to add extra oxygen. So an air management valve would actually send oxygen downstream to the catalytic converter to get it to run hotter, or to supply it with additional oxygen to combine with the bad gases. Because as you guessed, the catalytic converter's job is to take bad gases and turn them into good ones. And how do they do that? Well, if you take a CO and you put another O on it, now you get CO2, which is a greenhouse gas, but it's better than CO. Or you get H2O, and we'll talk about that. So what does a secondary air system do? It completes combustion. How does it do it? It puts air in the exhaust. Let's talk about the EGR valve next. It's really not that hard to understand unless you work for the bar in California. EGR means exhaust gas recirculation. You have what's called inert and volatile gases. Inert means it doesn't want to burn. Inert is the opposite of volatile, which means it will burn very rapidly. So gasoline, propane, pretty much anything that burns is volatile. Wood is volatile. Not as volatile as gasoline maybe, but it's volatile. Now any of these fuels, if you put in an oxygen atmosphere, if you took like a fish tank and you pumped it with pure oxygen and you put a cigarette in there, that cigarette is going to burn in seconds because there's so much oxygen. And remember, we're breathing about 21% oxygen right now. The oxygen coming out the tailpipe at stoichiometric is about 1.5%. So you can see the engine uses almost all the oxygen available for combustion. If the engine goes too lean, and there's too much air or it goes too rich, then of course we're going to have a different oxygen content coming out the exhaust, and that's what the O2 sensor does. One of the things the O2 sensor does is it can actually monitor system lean or system rich based on that oxygen content level. But getting back to the Egr valve, when the combustion chamber starts getting really hot, nitrogen and oxygen, which are the two basic elements we're breathing, about 79% nitrogen and about 21% oxygen, tend to melt together. That's above 2,500 degrees, and of course we've got pressures and everything else going on inside the combustion chamber. And it creates a gas called NOx. And we're going to leave it at NOx right now, NOx, N meaning nitrogen, O meaning oxygen, and then X could represent any number of oxygen atoms. And there is something called photochemical smog, and I'm going to mention this briefly. I believe it's NO4 is photochemical smog. So when it gets into the atmosphere, it combines with sunlight, and you get that brown haze. Back in the late 1960s and early 1970s, manufacturers were on the bandwagon about cleaning up these exhaust systems, and the ARB was created by Ronald Reagan in the late 1960s to clean these vehicles up. So getting rid of the road draft tubes that just vented the crankcase and combustion to the atmosphere, and putting in positive crankcase ventilation systems or PCV systems really cleaned things up a lot. But we had engines with big camshafts that were just blowing out raw hydrocarbons and COs. So they wanted to clean that up. So they started to lean these motors out, and put smog cams in. Smog cams are cams that don't have a lot of overlap. So when the piston goes to the bottom on a high performance engine, the intake cam stays open. And the reason it stays open is they want that column of air to keep ramming in to get a higher volumetric efficiency. That way you get more power. But the problem with that is at low RPM, the piston starts coming up and it blows that charge right back up into the intake, and the engine starts running rough, and then of course it puts out more emissions. So the smog cams came into effect, they leaned the carburetors out, and the problem was they were seeing more and more smog, which is a combination of smoke and fog. And I lived in the LA basin and I saw it. So they were scratching their heads what was going on, and what was happening is by leaning these motors out, they were increasing that combustion chamber temperature to the point that it created NOx. They melted the basic elements of the atmosphere, nitrogen and oxygen, together, and it created this photochemical smog. So in the early 70s, a lot of different EGR, or exhaust gas recirculation systems, were created to cool down the combustion chamber by taking gas that was already burned in the exhaust, which is inert because it's already been burned, and then redirecting it back into the combustion chamber would cool down that combustion chamber, and they could keep that temperature low enough so that the oxygen and nitrogen atoms weren't melted together, and therefore we didn't create NOx. The Egr system is very complicated. It connects the intake and the exhaust. It had a tendency to carbon up. Back in the 90s, there was all sorts of gizmos and devices to decarbonize Egr systems. They were troublesome because they were operating in really high temperatures. The whole Egr system was just kind of a nightmare, and Chrysler still runs it today. They water cool it in the JL, but it's still a nightmare. It's best to design the motor without it, but some engines still do run it, and it is an effective emissions device. One of the symptoms of losing your Egr valve could be knocking, because if the Egr system isn't working as designed, then the combustion chamber temperatures can get too high and lead to pre-ignition or engine detonation. So some people would call the Egr valve the anti-knock valve. But that's what it does, is it takes inert gas and it puts it back into the combustion chamber so that it cools it down and reduces the formation of NOx. It's interesting that I had some conversations with high-level bar referees and regional managers, and they had no clue how this system works, just like many other emissions inspectors across the country. So you guys are getting a little bit of a lesson. When you hear the word smog pump or anti-knock valve, now you kind of have an understanding of how it works, and you don't have to be afraid of it. I will say that the government did allow manufacturers to default to a failure mode where the emission systems were bypassed. So in an emergency, you had to floor it to pass somebody or get into trouble. Basically, all those systems are shut down. The air system, the Egr system, they would just shut down until you stopped flooring it. Now, the last one we're going to talk about is the catalytic converter, and that's probably the hardest one to understand. The catalytic converter came around in the 1970s, in the mid-1970s, and it does exactly what it says. It's a catalytic reaction where it takes bad gases and it turns them into good ones. So the definition, I would say, for the practical test would be, what does a catalytic converter do? It takes harmful gases and turns them into harmless gases. How does it do it? It combines elements with oxygen. So as we discussed, engines aren't 100% efficient. There's going to be hydrocarbons getting out, which is raw gas. There's going to be carbon monoxide getting out. And the bottom line is, whatever goes in the engine is going to come out the tailpipe. Now, how it comes out is what's important. Hydrocarbons can go in and hydrocarbons can come out. Oxygen can go in and oxygen can come out. But by combining these elements into harmless gases, that is the job of the catalytic converter. So whatever escapes the engine, I'm going to try to make this simple because the catalytic reaction is very complex. But basically, as the oxygen sensor switches at a certain frequency, the precious metals inside of the converter have little pores that store oxygen. And that oxygen is then combined with the gases going by. Like the COs, you add an oxygen atom and you have CO2. Or hydrocarbons, the carbon atom comes off, oxygen comes in, and you got H2O, which is water. And you guys probably see water coming out your tailpipe. Now, converters are a little more complex than that because there's basically three gases that they target. There's HC and COs, which are basically gasoline. They're a raw gasoline atom and a partially burned gasoline atom. If I were to describe CO, I would say it's like a marshmallow. If you take a marshmallow and it's all white and you put it into a campfire and you burn the edges and it's all black, but the inside's still white, that's a partially burned hydrocarbon or a carbon monoxide. So they have converters that target CO and HC. Well, that also leaves NOx. And remember, NOx is built at high temperature. So NOx is broken down under high temperature. So we have to have an upstream converter or closer to the exhaust that gets really hot to break up the NOx. The new engines have really intense converters. The LT converters are really large, but that's what the catalytic converters do. They take harmful gases and they turn them into harmless gases. So what would we do during an inspection? We would have to know how to identify these tampering devices. And it could be tough because EGR systems from different manufacturers and different states were different. Like if you took a Toyota with an EGR valve, they had the standard old pancake valve. And they had positive pressure and negative pressure EGR valves, where some opened up with vacuum and some opened up with pressure. But at the end of the day, they were all a little bit different. Toyota in California and other manufacturers started to run an EGS or an exhaust gas sensor to sense the exhaust gas to heat, how hot it was. And by doing that, they could more effectively run the EGR system. In fact, I think Chrysler is still running EGS in the JL. When you got an exhaust gas sensor running at 2,000 degrees, that's pretty intense. And you can imagine that the life of that sensor isn't going to be that long. And they were troublesome in the old days. And I remember Toyota, I think, at one point actually removed them and changed the programming because they ended up causing more emissions by not working. Now, there's ways to cool the EGR system off. Like the JL has a water-cooled heat exchanger to cool off the EGR system. But now we're just introducing more complexity again. By the 1990s, we had the linear and the digital EGR valves. They were electronically controlled. They put them on your intake manifold. You guys with the 4.6 and 5.4 Fords probably remember how troublesome they were because they had this long passage that would run up to the EGR valve that was connected to the exhaust, and they would carbon up. And when that carboned up, your EGR valve would become ineffective. And then you would start getting engine knock and trouble codes, and I'm glad those days are over. GM did run the linear valves. I don't know if you remember the old 4.3 Vortex and stuff. They were right there in the front. And it was an electronic valve. And over time, the electronic valve would lose its performance. And then it wouldn't open and you'd throw a EGR valve. Another problem was carbonization. Like I said, it would clog the whole system up and it required maintenance. The whole thing was just kind of a mess in my opinion. And designing the engine to not create NOx and using other technologies really was the way to go. In fact, General Motors has patented technologies on the LTs and the LSs to eliminate the EGR valve by using cam phasing. So you can actually phase the cam to cool down the combustion chamber by retarding it. And that way GM was able to eliminate the EGR system. And it's amazing to me that the LTs are running at 11.5 to 1 without an EGR system. And the CVVT, I think, is really what led to that being able to happen. So we would have to look at the EGR valve and make sure it was working. In some states like California, they did what was called functional testing. So they'd actually have to hook up a scanner, open the valve, and when you open the EGR valve up, you see a drop in RPM, and the reason is you're putting this inert gas back into the combustion chamber. So you're going to lose performance, and your idle's going to drop. So we had manuals that we would look these things up in, and the VEC could also help you identify the tampering components. because it would have a string of letters and numbers on it that would say things like O2 for like 402 sensors, and TWC, three-way converter, catalyst, and it would basically tell the inspector. And the California guys really need to look at these VECs, because when you're not willing to go to a manual and look it up, the VEC can be very convenient. After the Egr valve, let's look at the secondary air system. And again, this was a complex one. There were pump air and pulse air. Pump air was pretty simple. You just looked at the engine and saw if there was a pump on it. Now, later on, the Europeans started to do it early on, but later on, we started to use electric air pumps, and they'd hide them places. Even the GMs went to electric air pumps at one point. So you'd have to be able to identify the major components of the air system. You had the pump, whether it was mechanical or electric. You always had a check valve that would keep the hot exhaust gases from backing up into the system and destroying it. You usually had a diverter valve, and the diverter valve's job was you want to put air into the exhaust system under a load. You don't want to do it when you're idling or decelerating, or you might backfire. And I've seen mufflers blow off vehicles. So a diverter valve's job was to sense vacuum in the system and determine when it was under a load. A lot of people call them anti-backfire valves, but that's what they were doing. They were diverting the oxygen away from the exhaust under light load conditions, so you didn't backfire. So you have to be able to identify the components of the pulse air system: the pump, the smog trees, the check valve, etc. Pulse air systems could be complex also. Pulse air systems basically used vacuum from the exhaust to suck fresh air in. So as the exhaust gases were going through the exhaust pipe, you create a slight negative pressure that would suck that in. But again, you had to protect the system with a check valve. The Asians really got big into the pulse air systems because there was no pump. It was a simpler system, and there was no mechanical loss like there was with a pump air system. Even an electric pump draws some current. How do you inspect a catalytic converter? Well, that's not so easy. There are actually some functional tests for converters. A converter basically takes bad gases and turns them into better gases by combining them with oxygen. So the rear O2 sensors on your vehicle essentially are monitoring your catalytic converters. The amplitude of the waveform will be lower, and if you're running an air fuel sensor, an AFS, not so, but on a narrowband O2 sensor, the oxygen content in the front of the converter is going to be higher than the oxygen content in the rear of the converter, because it's using that oxygen to combine with other elements. Back in the 1980s, I knew a guy that was selling the catalytic converter test pipe. Remember the test pipes? You could buy them in all the magazines. It was meant to bolt in place of a factory converter so that you could see if your converter was plugged. Well, the reality is a lot of guys just left those tubes in and never put the converter back. So California quickly banned those. And there's some simple tools that you can use to see if your converter is plugged. You can remove the upstream oxygen sensor, run the engine, and look at the back pressure in the exhaust. Catalytic converters can be damaged pretty easily. They can be overheated and melt. You could dump fuel into them and carbonize or coat that layer of precious metal that has the pores in it to store the oxygen. And once that's coated, you're pretty much screwed. It's not going to work anymore. But your rear O2s will pick that up. It'll pick up that the converter's not doing its job. As far as the configuration of the converters, 2 converters, 1 converter, a NOx converter, HCCO converter, you guys got to go to the manual and see how the manufacturer had it certified. We don't got to talk much about the fuel restrictor and gas cap. That's pretty easy. You just look at the fuel restrictor and make sure it's there in place. There used to be a tool to measure it to make sure it wasn't punched out, and the gas cap is there. I know here in Nevada, when I was an emissions inspector, the coverts. A covert is a guy that works at the lab, and he goes around getting emissions inspections from inspectors and tries to catch them up. Like, did they see that the check engine light wasn't coming on? But the gas cap was a big one. What they do is they drill a small hole through it, and they go all the way through, so it was obvious that the cap wasn't sealing. And a lot of guys didn't pick that up. Other times they just pull the seal off. There's a rubber seal, and sometimes it looks like that seal doesn't have to be there. And again, guys would fail their covert because of that. So those are the 5 basic tampering devices we would look for. On the onboard diagnostic 2 test, what happens is the analyzer pulls the data out of your computer, because as you've been driving, the monitors have been doing their job. They're the ones doing all the diagnosing. So we're not doing off-board testing where we're hooking it up to a lab scope for a secondary. Most states, we're not putting a tailpipe in and measuring the gases. The old tailpipe test physically measured the amount of gas that would come out. Now, California, they do that. And their standards are pretty tight. I think they're 120 parts per million on the hydrocarbons, and it's like 220 everywhere else. Maybe it's 110. CO is measured in percentage. Most of the states allow 1.2%, and I think California is down at 0.6%. But the bottom line is, most of these modern engines run much cleaner than that. Most of these modern engines blow zeros when they're set up properly. The hard part for an emissions inspection is getting an inspector that knows what he's doing. And as an emissions inspector for a lot of years, it's really experience, not bookwork, that lets you do it right. Because every manufacturer is different. The way BMW did their electronic PCV valves and Cadillac did their Egr systems that were different than everything else, you just got to learn that stuff from experience. They all pretty much end up doing the same thing and getting the same result, but they do it in different ways. And just like mathematics, when I grew up, we had to use the slide rule, we had to use mathematic tables and calculate things like logarithms in school. Today, everything is based on a computer or a calculator. And that's what smog inspectors are doing, is they're just plugging in and they're looking at data like PDTCs, permanent trouble codes, and DTCs, and see if monitors are set. But they're kind of losing the art of what emissions really are. And they're not understanding how these systems work. And I run into it all the time. I run into guys that, whether they passed or they failed, the emissions inspector will say something and it's completely wrong. Labs in general, but especially California, covers up their mistakes. They usually won't admit them. The problem is the public at large isn't trained in these systems, so they don't know how to argue. If a referee or a manager tells you that you're illegal because of this, this, and this, you have to believe them. Now, I dispute these guys all the time, and they back down. And in some cases, there actually is a failure. But I can say way more often than not, there isn't a failure, and there's a misunderstanding or incompetence on the part of the inspector to do the emissions inspection process. Sorry guys, I'm back on my cell phone. I've been rambling too long, and the SD card ran out on the GoPro. When I get on emissions, I really start to ramble, but it is an important subject, and it's a subject that's going to get more and more important as time goes on. So what I'll do is I'll devote a couple of more videos to this, especially trying to get compliance in some of the more difficult states like Colorado and California. And yes, we have executive order bills that have been approved and registered in states like Colorado and California. Colorado just started doing their executive order requirement recently, and we've already had one passed, so we're proud about that. California is a whole different world, and we're going to talk about that in another video. I tried to go a little slower on the trail with this Jeep so that I could stretch out the monologue part of this. So stay tuned for the next video. We'll be back.